Hello, this is Mr. McGovern. This is the fourth video in the Balanced Talk series where I'm going to tackle an NCEA problem. So this NCEA problem is from 2021. It's question 3 and there's 3 parts to it that I'm going to answer. So the first one is B. There's a rider rides over a 4 metre long bridge and stops 3 metres from the end. The bridge has a mass of 700 kgs and the combined mass of the rider and the bike is 85. So there's a picture of a bridge there, which isn't shown because of their silly copyright things. But anyway, the first question says, state the conditions required for the bridge to be in equilibrium. So there's 2 conditions, and they are the forces on the bridge must be balanced. That means that the bridge isn't accelerating upwards, or it's not accelerating downwards, or accelerating left or right. And the second is that the torques on the bridge must also be balanced. That means the bridge is not rotating, so it's not collapsing from one end or another. So now they want us to draw labelled arrows to represent all the forces on the bridge. So they've said that the cyclist has stopped, even though the picture there does not look like the cyclist has stopped, but the cyclist has stopped, so we can assume there's no horizontal forces. The forces are just going to be up and down. So the obvious one is the force of gravity from the bridge. That acts through the middle of the bridge, so it's 2 metres from the end, so that's because the bridge itself has weight. The second is the force from the cyclist standing on the bridge. Now that is a normal force. It's not a gravity force because the earth pulls down on the rider, and the rider interacts with the bridge via a normal force, because a normal force is a force that is 90 degrees to the surface, and you can see the surface of the bridge is that way. There'll be a normal force on the bike rider upwards from the bridge, and then the normal force I've drawn is from the bike rider on the bridge downwards. There is a normal force from B, which is holding it up, and there's another normal force from A as well. So I've also, you can see I've got different sizes here. The mass of the bridge is 700 kgs compared to the mass of the rider was only 85, so I've made the rider's force much smaller. And because the rider's on the left-hand side, near support A is holding more up than support B, so I've made that force slightly bigger than the one at force B. Okay, so now it says calculate the values of all these forces. So I've just kind of simplified them here. All the forces here that I need to calculate. So I've got force A, force R for force rider, force gravity, and force B. So to solve these problems, there's an algorithm that we go through a set of instructions where we label our diagram, which we kind of have. We choose a pivot point, identify the clockwise and anti-clockwise torques, write an equation, and solve it. So the first one was to label the diagram. Even though I've got this labelled, I can label it further because I can work out some of the forces quickly now. For example, the force of gravity on the bridge is just mass times gravity, 700 times 9.8 newtons per kg, and multiply that together gives me 6860. So I'm going to add that to my diagram. I can similarly have worked out the one for the bike rider, which was 85 times 9.8, and add that to the diagram as well. So now we've got 2 of these worked out. Now I'm going to use torques to work out the rest. So I choose a pivot point. I could choose either A or B. I'm just going to, for argument's sake, choose A. Now I identify the clockwise and anti-clockwise torques. So I imagine that bridge pivoting from that point. So it could pivot down clockwise like a second hand on a clock, pivoting at the point, or it could go the opposite way. So what would cause it, or try and pull it around the clockwise direction? Those 2 forces. They're trying to pull it down the clockwise. What's trying to pull it anti-clockwise? That force, the force of B. And what we know is that the bridge is not rotating clockwise and it's not rotating anti-clockwise because those 2 forces or torques trying to rotate it down are being cancelled by the torque trying to pull it up. And so I can write that as an equation, that the torques balance. So my clockwise torques are balanced by my anti-clockwise torques, and my clockwise torques are the torque from my rider and the torque from gravity, and it's balanced by the torque at B. Now, torques, when we go to solve this, torques are equal to force times distance. So I can't just say that 833 plus 6860 is balanced by some force. I've really got to make sure I'm doing the torques, which is force and the distance combined. So my equation, torque R plus torque G equals torque B, I'm going to sort of expand that for each of those torques. I'm going to work out what that torque is. And that is So the torque of the rider is equal to the force, 833, times the distance back to the pivot point, always to the pivot point. And the distance from the rider to the pivot point is 1 metre. My force of gravity is 6860, and it's 2 metres back to the pivot point. And that equals my torque from B, which is the force of B times the distance 4 metres back to the pivot point. And I can rearrange that and solve that, and if I do, I get force of B is equal to 3,600 newtons. If I wanted to, I could go through the same process but have chosen my pivot point to be point B, and then I could have worked out the force at A. However, there's another way. The other way to work out the remaining force is just to look at the balanced forces and say my upwards forces, force A and force B, is balanced by my downwards forces, force R and force G. I've got a bunch of them already. I know force B, 3,600. I know force R, 833. I know force gravity, 6,860. Rearrange that to get force A, and I get 4,000 newtons, which is slightly bigger than B, which is what I expected. So the first two problems that I did state the conditions for equilibrium. I think might have been a merit for both of those. The second one where you had to draw the forces was definitely a merit, and this last one where you had to work out all the forces was an excellence problem. I hope that helped.